So we're going to talk about 3.3 zeros of a polynomial. We've done some synthetic division. What I want you guys to also remember is to find x-intercepts. You set f of x equal to 0. This is the same thing that we've always done. And then the definition of a polynomial function is a function with real number coefficients and whole number exponents. So you're not going to see any square roots, or you're not going to see any rational function type stuff like a function divided by a function. So back to this solving f of x equals 0. When we're talking about polynomial functions, we've already done some quadratic stuff. We're really kind of looking at x cubed and beyond. Solving this polynomial equation is easily done if we can factor it, but factoring a polynomial may not be easy. So here's a list of the theorems that we cover in 3.3, and if you're looking at these notes, the first page is some synthetic division stuff, and then it goes into a lot of these that we're going to talk about in 3.3. The one up here that this is in the synthetic division section is the remainder theorem. So check that out from the synthetic division section. It's a pretty straightforward theorem, but the factor theorem ties into that, so we're going to talk about both of those kind of at the same time. So the whole goal of this section is to end up being able to figure out the x-intercepts of a polynomial function. This right here is just a generic way to write a polynomial. So you have a leading coefficient, x to the nth, whatever whole number that might be, another leading coefficient, and then one less than the highest power. So the highest power, let's make a note, the highest power is the degree of the function. So if this is if n is 5, then that's a 5th degree polynomial, and then written in descending order, then the next term would have an x to the 4th. If the coefficient of x to the 4th is 0, then you would go to x to the 3rd if it had a non-zero coefficient. So here we're looking at a function that is factored. And like I said, we can solve this equation. We can find the zeros of this polynomial easily if it's factored. This is a 4th degree, so jot this down. The reason this is a 4th degree is because if I multiplied this out, I'd have x times x times x times x, which would give me x to the 4th. And there's a 1 in front of all of these right here, so the leading coefficient would be 1. So this is a 4th degree polynomial, so it's going to have 4 solutions. And if it's factored, we can look at it really easily and see the solutions. 1 minus 1 would be 0, so if this entire thing were set equal to 0, x equals 1 is the solution. So what the factor theorem tells us is if we plug in 1 and we get out 0, that tells us that x minus 1 is a factor. So we're looking at a factored polynomial. That's x minus 1, the factor x minus 1. Therefore, if we plug in 1 into the function, the output has to be 0. So if we look down here, another way to write that is if we take the function and divide it by x minus 1, then we are going to get a function which is 1 less degree, so in this case a 3rd degree function, plus a remainder, where the remainder is 0. And you guys have all canceled common factors. So if I have x minus 1 times x minus 2 times x minus 3 times x minus 4 divided by x minus 1, cancel those out, and you're left with this right here, with the remainder is 0. So that's all the factor theorem says. It kind of ties into the remainder theorem from the previous section, where it says that if you plug in a number into the function, the remainder from synthetic division is equal to the output. So the remainder theorem here would say that the remainder is 0 when you divide by, or when you plug in 1 into the function. So the output of the function is the remainder. Excuse me. Okay, the next one is the rational zeros theorem. When we say rational zeros, we mean rational numbers. So a rational number is an integer over an integer, and zeros are the same thing as saying roots. So zeros don't mean the number 0, it means the values for x that make the output of the function 0. A synonym is roots. So this is best described or best taught just by giving you an example, and then we can look up, I think on the first page I had everything written down on where everything was in the book. So factor theorem is on 327, rational zeros theorem is on 328. So I'm going to show you how this works, and then you can read about the kind of the technical statement of the theorem. But this is a test question. It should also be on the final. We're just making a list. So we're not going to go through and do 20 rounds of synthetic division here. We just want to make a list of all the rational numbers that could solve the equation f of x equals 0. What that means on the graph is we're giving all possible real number x-intercepts. So what we do is we take the factors of the constant. So this is the constant. And you include the number itself, and you always include 1. So 5 is prime, so the only factors are plus or minus 1 and plus or minus 5. And 2, my least favorite number, as you guys know, because it is the only even prime number. We take the factors of the leading coefficient, and we do the same thing. So plus or minus 1, plus or minus 2 are the factors of the leading coefficient. Then all possible rational zeros are a combination of the factors of the constant divided by the factors of the leading coefficient. So let me write that out. So this is a sloppy way to write the answer, but we can see what's going on, and then we're going to make the list. So all possible rational zeros, this is what the rational zeros theorem says, are any combination, or all of them, are all combinations of the factors of the constant divided by the factors of the leading coefficient. So you've got all of them are plus or minus, so I just generally put a plus or minus out front. So you've got 1 over 1, and then 1 over 2, then you've got a 5 over 1, and a 5 over 2. In Math Excel, you're probably not going to put a plus or minus. In fact, I don't even think there is a plus or minus button in Math Excel. So you're going to write 1, comma, negative 1, 1/2, comma, negative 1/2, and all that. So this is the answer to that question. You're not doing anything else with it. This question is just asking, it's just seeing if you know how to use the rational zeros theorem. And we're going to go further with this stuff once we've kind of put everything together, but that is the question in itself. So you just make that list. So the fundamental theorem of algebra, to me, is extremely fascinating. To you guys, it probably won't be. Gauss, a famous mathematician, proved this. The statement is so simple, but how you can prove this, and make it a theorem and make it a law is, to me, it's fascinating. So every non-constant polynomial has at least one complex zero. So remember that all numbers are complex numbers, so a plus bi is a complex number. We just say it's a real number if in a plus bi, b is 0. So 5 is a complex number because it's 5 plus 0i. Now, if it's a pure complex or pure imaginary, b would not be 0. So a pure imaginary would be if a is 0, so like a plus bi, 0 plus 3i. or something like that. So this means zeros that include i's and zeros that aren't necessary, don't have i's, which means, you know, just real numbers. This theorem, we do everything that we do is because of this theorem in this chapter. So like I said, it's a super simple statement. Every polynomial, every non-constant polynomial has at least one solution. So that leads us, and just the knowledge of that is what allows us to solve all these you know, polynomial equations and things like that. But yeah, that's the fundamental theorem of algebra. Sounds pretty important, is pretty important, but that's all we really need to do with it, is state it. But that leads us right into the number of zeros theorem. I'm going to put this on a different page. So a little more specific, and then, you know, because we're going to apply this stuff, is, okay, where do we go from the fundamental theorem of algebra? A polynomial of degree n has n complex zeros. So that could mean, you know, a plus bi, where b is not 0, so you actually have a, you know, a complex number, or real numbers, or combinations between you know, real and pure complex. So if it's x to the 6th, that means that there are 6 solutions to the equation f of x equals 0, and we call those roots. So what we can say here is, if this factors into, let's say, x to the 6th plus 3x minus 7 equals x minus k1, x minus k2, x minus k3, and so on and so forth. So I would do that 6 times. I'm out of paper. I don't want to write 3 more binomials. But if we factor this out into a product of binomials, the solutions are x equals k1, k2, k3, all the way up until 6 of them. And as you guys know from solving quadratics, they could repeat. So if 2 is a solution, and but the factor has like 2 squared or something like that, or if k1 and k2 are actually the same number, the solutions can repeat. They're going to add up to 6. So the goal here, keep in mind, is we're ultimately going to graph polynomial functions which require real number x-intercepts. So we don't plot complex x-intercepts, we're only graphing in the real number system. So we're going to end up trying to figure out the real number roots, because those get plotted on the graph and we can sketch the polynomial. And another, following the number of zeros theorem, is the conjugate zeros theorem. It's also commonly called just the property of complex conjugates. And this is on page 332. This is a pretty chill theorem also. So if we have complex roots, and we say a plus bi is a 0, then a minus bi also has to be a 0. So for example, if I said if we have a degree 2 polynomial and that x equals 2 plus 7i is a root, find the other root. Interchange root and 0 whenever you want in terms of 0 of a polynomial, root of a polynomial, those are synonyms. So if we know that 2 plus 7i is a root, and this is a second degree polynomial, so the total number of solutions is 2, if it's degree 2. So then the other solution is 2 minus 7i. So that's a pretty straightforward and pretty simple theorem to use. But let me give you an example of that. So you guys from the last section, you guys can solve this. What we would do I think everyone's probably good with that, but let's take a look at this. So factoring x squared plus 5, we'd be like, I don't know. It doesn't have real number factors, so we really don't even want to mess with factoring it. But let's say we have x minus 1 plus 2i, and then x minus 1 minus 2i. So we're going to simplify this and multiply it out, and we're gonna take a look at how this property of complex conjugates works. Actually, let's just make this a little easier, so I don't have to multiply out trinomials. I can accomplish the same thing here by just multiplying these out. So let's multiply, and when we mean conjugate, it means if this is 1 plus 2i, its conjugate is 1 minus 2i. So let's multiply that out. 1 times 1 is 1. 1 times negative 2i is negative 2i. Positive 2i times 1 is positive 2i. And then 2i times negative 2i is negative 4i squared. So then if we simplify that, we're going to have 1 minus 4i squared. Now remember, I is the square root of negative 1. So 1 minus 4 times negative 1. So I squared is just a fancy way to say negative 1. So 1 plus 4 equals 5. So we actually just showed that we can factor 5 into these complex conjugates. So x minus 1 plus 2i, and then x minus 1 minus 2i, this would show that if 1 plus 2i is a 0, then 1 minus 2i has to be a 0, and then rather than multiplying out that trinomial and getting back to that x squared, I just multiplied these out so we can show that 1 minus 2i times 1 plus 2i is 5. Descartes' rule of signs. So you pronounce this Descartes. René Descartes, French mathematician, came up with this. This is a really powerful tool. It's kind of hard for some students to get the hang of, so I try to put this in plain English as possible. Okay, so the first half of this is we're going to find the possible number of positive real zeros. So this isn't telling us what those zeros might be. This is telling us how many to look for. So we're kind of going fundamental theorem of algebra and following, that trail, and getting to, okay, let's say that we have a degree 6 polynomial. how many possible roots are positive, how many possible roots are negative, and we know that they have to add up to 6. So, you know, that we're kind of just putting all these tools in the toolbox, and we'll take them out of the toolbox and use them as we see fit in the next section. So to find the possible number of positive real zeros, we count the sign changes. We count the sign changes in f of x. So let's say f of x is negative x to the 4th plus 2x cubed minus 6x squared plus x plus 8. So if this is the function, we are going to count the sign change. And what we mean by a sign change is for a polynomial function that is multiplied out, written in descending order. So for whatever reason you're given a polynomial that where like the x squared is here and the x cubed is here, rearrange it, write it in descending order. A sign change is where coefficients of terms in descending order go from positive to negative or negative to positive. So that's what we call a sign change. So we're going to count those. So we have a negative x to the 4th to a positive 2x cubed. We're going to go from a positive to a negative right there. And then a negative to a positive. So there's 3 sign changes. What Descartes' rule of signs says for the positive real zeros is and this is for real number zeros. So what we do is we take the number of sign changes, and then it's either that number or 2 less than that all the way to 0. And 0 is always an option. So let's say we had 8 sign changes. Let me just write this down. If we had 8 sign changes, number of possible real zeros are 8, 6, 4, 2, and 0. So it's always the number of sign changes and then minus 2, minus 2, minus 2 until you get to 0. If it starts with an odd, you're going to get to 1 when you keep subtracting 2, but 0 is always an option. So be careful in Math Excel. Make sure you enter 0 unless read the instructions, but 0 is always a possibility for Descartes' rule of signs. So that takes care of the positive side of the number line. Now we need to do the negative side of the number line, and we can accomplish that by looking at f of negative x. So the possible number of negative real zeros. So let's see, we had f of x equals negative x to the 4th plus 2x cubed minus 6x squared plus x plus 8. We need to compute f of negative x. So we've already answered half of it, positive side of the number line, but to get to the possible number of negative real zeros, we need to first compute f of negative x. Now, don't work harder than you have to. Anything to an even power is always, the sign isn't going to change. So like negative x, the quantity to the 4th power, is still going to be x to the 4th. So an easy way to do this is change the signs on anything with an odd exponent, because you're always going to have, a negative left over in that multiplication. So anything with an odd exponent gets a sign change. F of negative x is right here. Now count sign changes. We only have 1. And now the same rule applies. It's the number of sign changes, minus 2, minus 2, minus 2, until you get to 0. So 1 or 0 possible negative real zeros. So let's say there were 9 sign changes in f of negative x, then that means there are 9, 7, 5, 3, 1, or 0 possible negative real zeros. So 9, if there were 9 sign changes in f of negative x, this is the negative side of the number line, then that means there are 9, 7, 5, 3, 1, or 0 possible negative real zeros. If we look at our original function, we've narrowed down what we're looking for in terms of the real zeros. On the positive side of the number line, we knew that there were 3, 1, or 0. On the negative side of the number line, we know that there's either 1 or 0. So we can kind of use that information to start figuring out, narrowing down our list of possible zeros to that function. So for example, if we did some synthetic division and we found 1 negative real zero, that's enough information to tell us that there has to be 3 positive real zeros because they have to add up to 4. Assuming there's no complex. Now, also remember, let's suppose that there are complex zeros. That complex zeros comes in pairs. So let's say we found a complex 0. Well, if we know that there is one complex 0, if we know that there is one complex 0, such as 2 plus 7i, well, it has to come with its pair. 2 minus 7i also has to be a 0, so then we can narrow down our list and say, well, I know that there are 2 complex zeros, so that must mean that there's one positive real zero, and then we had 1 negative real zero was a possibility. Then we can just use that to narrow it down. If these problems aren't nice, it can get extremely tedious and monotonous to continue doing synthetic division. So like, for example, if I gave you a 12th degree polynomial and you had a list of 20 different factors that or 20 different zeros that could be possible from the rational zeros theorem, this can get extremely tedious. So the author in the book, I know, writes pretty good, pretty straightforward. You might have to do synthetic division a few times. And same thing on the test. Like, I think if you can do it for like a 4th or 5th degree, you could do it for a 10th degree. So just be aware that if you're trying to figure out, for example, how many zeros there are and you have to do some synthetic division, just be aware that you might have to do it a few times. It's not super exciting, but it's part of this chapter. And then the only other thing, I think it's in the next section. Yeah, so if it's in the next section, I'm going to stop because I'm recording and I'm doing section by section. And we're getting close to time here. So let's see if I can zoom in and you guys can see this document here. So if you go through these up to Descartes' rule of signs and follow along with these, this will help you out with what we're doing today prior to doing your Math Excel homework. Okay, that is section 3.3.